In Samurai Age Japan, a castle was never built against armies alone. It also had to face an enemy no wall could see coming, the ground beneath it. From below, Kumamoto Castle looks impossibly rigid. Its stone ramparts rise in severe curves, holding a fortress that seems too heavy for a land of earthquakes. But the deeper secret was not rigidity. It was controlled movement, pressure, friction, weight, and the quiet ability to yield before breaking. These walls were not truly earthquake-proof. No building is. But they were designed with a resilience that feels startlingly modern, absorbing force instead of simply resisting it. To understand that logic, we enter Kumamoto Castle, one of Japan's most formidable fortresses, and look beneath the elegance of its black and white towers. Kumamoto was more than a residence. It was a defensive machine, a political symbol, and a masterpiece of castle engineering in a region shaped by restless earth. Its great transformation is tied to Kato Kiyomasa, the daimyo and castle builder who expanded the site in the early 17th century with rare strategic intelligence. Japan sits along some of the most active tectonic boundaries on Earth. For builders, the enemy was not only the army at the gate, it was the island itself. A wall made too stiff may appear powerful until the Earth starts moving. Then stiffness can concentrate stress, and strength becomes a trap. The Japanese answer was more subtle. Instead of forcing every stone into perfect obedience, builders allowed the wall to act as a system. These ramparts are known as ishi-gaki, stone walls built from enormous rocks, selected, angled, and stacked so gravity becomes part of the structure. In many sections, mortar was not the main binding force. The joints, gaps, and imperfect contacts were not errors. They were part of how the wall behaved. When shaking began, stones could shift slightly against one another. Friction, mass, and contact spread energy through the wall instead of locking it in one brittle body. That did not make Kumamoto invincible. The 2016 earthquakes proved the castle could still suffer terrible damage. But the old logic of resilience remained visible in what survived. The most famous form at Kumamoto is called musha-gaeshi, the warrior-repelling curve. It begins almost invitingly, then steepens until climbing becomes impossible. To an attacker, the curve was intimidation. To an engineer, it was geometry. Weight pushed downward, pressure spread outward, and instability carefully controlled. The curve did two jobs at once. It made the wall nearly unclimbable, and it helped the stones lean into the earth behind them. Behind the beautiful face of stone was a hidden mass of earth and gravel. This was not a thin wall. It was an artificial mountain wrapped in masonry. Every stone mattered. Large stones anchored corners and gates. Smaller stones filled voids, adjusted pressure, and allowed the rampart to settle over time. At the corners, the craft became even more exact. Stones were interlocked across two directions, creating edges that could hold enormous loads. These corners were the bones of the fortress. If they failed, gates, turrets, and passages could lose their support and slide into the slope below. Above the stone base, the traditional castle architecture was lighter. Timber frames, wooden posts, and joinery could respond to small movements in ways stone never could. Wood bends, it creaks, it shifts. In earthquake country, that flexibility was not weakness. It was a survival strategy hidden inside elegance. Long before modern seismic terminology, builders understood a practical truth. A structure that moves a little may survive forces that destroy a structure that refuses to move. The genius was the relationship between materials, stone below, earth inside, timber above, each taking stress differently when the ground changed. Building such walls required more than strength. It required moving stones so heavy that every transport route, ramp, rope, and lever became part of the design. One badly placed boulder could weaken an entire face. The builders had to understand where weight should fall and where force would travel. They were not chasing perfect symmetry. They read each stone like terrain, its grain, its shape, its fracture lines, and the way it could grip its neighbors. Some stones remained rough to lock through friction. Others were shaped more carefully near gates, where military pressure and structural pressure met. This was engineering born from war. The walls had to resist ladders, fire, arrows, and siege. But they also had to survive the silence before a quake. That silence broke in April 2016, when a sequence of powerful earthquakes struck Kumamoto and exposed both the brilliance and the limits of the castle's old design. Stone walls collapsed in sections. Turrets shifted. Roof tiles fell. The disaster showed that resilience is not the same as immunity. Yet the damage revealed something extraordinary. Many fallen stones remained identifiable, as if the wall had broken into pieces of its own memory. Restorers began treating Kumamoto like a three-dimensional puzzle, comparing stone shapes, historical records, old images, and the surviving logic of the ramparts. At Kumamoto, restoration is not only repair. It is an attempt to reconstruct the thinking of the original builders, stone by stone. The scale is immense. Rebuilding means returning weight to the correct place across vast wall surfaces, one heavy fragment at a time. Here, old and modern knowledge meet. Engineers study deformation and ground conditions, while craftsmen read the ancient grammar of dry stone masonry. The deeper question is not simply why some walls fell. It is why so many parts endured for centuries in a landscape that never stops moving. Modern engineering often tries to eliminate failure. Historical dry stone construction sometimes allowed small movement to prevent total collapse. An ishi-gaki wall is not one solid block. It is a dense field of interacting bodies, where every contact point changes how force travels. Energy can move through gaps, joints, friction, and compression. Before collapse, the wall can deform, redistribute stress, and buy time. That idea sounds modern, yet it emerged from centuries of observation, disaster, rebuilding, and necessity. Kumamoto's walls also worked on the mind. Their rising curves made attackers feel small, while the keep above seemed to hover beyond reach. The same curve that defeated climbers created one of the most elegant silhouettes in Japanese military architecture. Here, defense and engineering became art. Each slope, gate, corner, and tower belonged to a larger choreography of danger and design. To move through Kumamoto is to move through calculated uncertainty. The fortress turns, narrows, rises, and hides its strongest points until the last moment. Attackers would be delayed by angled routes and exposed from above. The ground's violence, meanwhile, would meet stones arranged to shift burden through the slope. Nothing here feels accidental. Even irregularity has a purpose. Even beauty is doing structural work. One myth of architecture says permanence comes from resisting change. Kumamoto suggests something deeper. Endurance may come from accepting movement. That is why the castle feels strangely alive. Its stone skin, earthen core, and wooden body each answer the same invisible force in different ways. The 2016 earthquakes did not erase Kumamoto's story. They opened it, revealing construction secrets usually hidden behind centuries of stability. Every fallen stone became evidence. Every crack recorded direction and force. Every surviving corner became a lesson in endurance. Restoration now carries a difficult responsibility, preserving the old logic while making the monument safer for the future. If rebuilt too perfectly, the wall may lose the wisdom of irregularity. If rebuilt too loosely, it may fail again. The balance is delicate. That is the hidden drama of Kumamoto Castle today, not just bringing back what was lost, but understanding why it stood for so long. The old builders left no equations carved into the stones. Their knowledge survives in curves, gaps, weights, and a wall that was never truly still. Perhaps that is why these ramparts remain so powerful. They do not promise that nothing will fall. They show that survival can be designed through adaptation. Samurai Age Japan did not defeat earthquakes. It learned to negotiate with them, using gravity, timber, stone, and patience as its language. The impossible wall was never impossible because it refused to move. It was impossible because it knew how much movement it could survive. And in those ancient stones, Kumamoto leaves a lesson that still feels modern. Sometimes the strongest thing humans build is not what resists the earth, but what moves with it.